Good morning, members of Geology Society of Malaysia. Thanks to Dr. Hariri's invitation for this presentation. The title is, Geothermal Exploration and Production. This is a very general subject. I will also include two special geophysical exploration methods in geothermal development which we developed. Before we start, I would like to share with you about the celebration of Lardrello of Italy for its 100th anniversary of the first commercial geothermal power plant in 2020. The contents of today's presentation are: first, introduction of 3J Tech and the founder, that would be me. Second, geothermal direct uses and power plants. Third, conventional and unconventional geothermal system. Fourth, geothermal development program. Fifth, a volcanic and non-volcanic related geothermal reservoirs. Sixth, financial assistance from the government in Taiwan and Japan. Seventh, why magnetotelluric exploration is needed in geothermal development. 8th. Advantage of 3J-Tech's magnetotelluric array. 9th. Comparison of magnetotelluric array results with the drillings in Taiwan. 10th. An extended linear ramp control source electromagnetic or ELR_TEM exploration and its potential application in geothermal. This slide shows my curriculum vitae. I got my scholarship from Taiwan Ministry of Education in 1977 to study at Colorado School of Mines and was the research associate for few years after I got my PhD in geophysics in 1980. I started my company called Geo-Pacific Resources, Inc., or GPI in 1982 in Denver, Colorado using the hardware and software we developed for electromagnetic geothermal and unconventional oil and gas exploration services. The main system is the control source electromagnetic exploration. In 1988, 3J Tech was established in Taipei, Taiwan. In 1996, GPI was merged into 3J Tech. This slide shows the field sites we had carried out for the past years. Mainly are for geothermal exploration in Japan. The red ink represents sites which has sizable geothermal power plants built so far as I know. This slide show the patents which we owned. I hereby summarize 3J Tech's company history. In 1982, established Geo-Pacific Resources, Inc., in Denver, USA for control source electromagnetic exploration services. Explored more than 30 geothermal sites and a few geothermal power plants have been built from our services. In 1988, established 3J Tech Company, Limited, a subsidiary company of Geo-Pacific Resources, Inc. In 1993, GPI was merged into 3J Tech which design and manufacture communication, network products and instruments. In 2010, design and mass produce a new generation of geophysical exploration system, which is dedicated to geothermal exploration systems in complex terrain, high population density and traffic-intensive areas and for oil and gas exploration in seismic difficult areas. In 2015, launched our new generation of geophysical system. Exploration services were conducted in Taiwan, China, Japan, Korea, and the Philippines. In 2016, applied our new developed system and identified several geothermal reservoirs in Taiwan. In 2019, promoting geothermal reservoir data to the investors for developing the identified reservoirs. Currently, 3J Tech is capitalized at 171 million new Taiwanese dollars, which is about $6.15 million US. Now I would like to talk about the usages of geothermal. There are mainly two scenarios. One is the direct use. On the left side of the slide, it shows examples of geothermal direct uses. On the right side of the slide is the temperature ranges for different types of geothermal applications. One interesting subject is that geothermal could be used for cooling in addition to heating. I think this might be an useful application in Malaysia and Taiwan. Cooling is usually needed in housing and buildings in Malaysia and Taiwan. Now I would like to present the different types of geothermal power plant. The first type is the dry steam power plant. Dry steam power plants draw from underground resources of steam. The steam is piped directly from underground wells to the power plant where it is directed into a turbine and generator unit. There are only one known underground resources of steam in the United States, which is the geysers in Northern California. It is the world's largest geothermal power plant and has 1,590 megawatts capacity. The second geothermal power plant type is the flash steam power plants, which are the most common and use geothermal reservoirs of water with temperatures greater than 182 degrees Celsius. This very hot water flows up through wells in the ground under its own pressure. As it flows upward, the pressure decreases and some of the hot water boils into steam. The steam is then separated from the water and used to power a turbine and generator. Any leftover water and condensed steam are injected back into the reservoir, making this a sustainable resource. The third type of geothermal power generator is the binary cycle power plants or organic Rankine cycle generators, which operate on water at lower temperatures of about 70 to 182 degrees Celsius. Binary cycle plants use the heat from the hot water to boil a working fluid, usually an organic compound with a low boiling point. The working fluid is vaporized in a heat exchanger and used to turn a turbine. The water is then injected back into the ground to be reheated. The water and the working fluid are kept separated during the whole process, so there is little or no air emissions. Now I would like to talk about the two geothermal systems, the conventional one and unconventional ones. I separate the conventional one into two groups. The first one is the volcano-related, the second one is the non-volcano-related. The volcanic-related geothermal systems have three main criteria. It needs to have heat source, for example near caldera. It also needs to have caprock, which is clay, and the aquifer below. The non-volcanic-related geothermal reservoir has no clear heat source nearby. Maybe from deep magma. The reservoirs are usually fault and fracture-related. There are two recent developments in unconventional geothermal systems. The first one is the Enhanced Geothermal System or EGS, which injects water at high pressure into these deep rocks to reopen the natural fractures and allow hot water or steam to flow into extraction wells. In the figure of this slide, 3 continuous injection wells keep these fractures open and provide a constant source of water to be heated up and extracted for electricity production. The second unconventional geothermal system is the closed-loop geothermal systems, known as Advanced Geothermal Systems or AGS, are also gaining traction in the industry. In the recent years, 3J Tech has been trying to develop geothermal power plants in Taiwan. This slide shows our development process. It is separated into 2 phases. The processes in the first phase are non-obtrusive data collection to locate possible reservoir, magnetotelluric array explorations to locate probable reservoir and build the preliminary geothermal conceptual model, acquire lands and apply government subsidy and funding. The processes in the obtrusive second phase are to drill to prove the reservoir and modify the conceptual model, build small experiment geothermal power plant of about 500 kW or withdraw the development or jump into production well drillings, build sizable geothermal power plant, collect well and power plant parameters and modify the reservoir model. This slide shows the locations of the 3 geothermal power plants under construction in Taiwan. Also show is the location of our developing site. Our site is volcano-related, which is about 2 km away from a caldera. The remaining 3 are non-volcano-related. However, the 2 non-volcano-related site in the northeastern of Taiwan has a deep magma nearby as shown by the Airborne Magnetic Survey. These photos show the geothermal power plants in Taiwan which are all under construction. They all use binary cycle systems. This slide shows the financial assistance for geothermal development in Taiwan. For the exploration stage, the government subsidizes up to 50% of the exploration and drilling cost. The maximum subsidy is about $3.57 million. 3J Tech's developing site got about $2.99 million subsidy from the government. At production stage, the government-owned power company has the 2 options of procuring the electricity generated by the geothermal. The first option is US 22 cents per kilowatt-hour for the first 10 years and 11.8 US cents per kilowatt-hour for the second 10 years. The second option is 18 US cents per kilowatt-hour for the 20 years. This slide shows the outline of financial assistance for geothermal development in Japan. The difference is that the key player is the Japan Oil, Gas and Metal National Corporation or JOMEC instead of the non-technical government officers like what is happening in Taiwan. JOMEC has geologists, geophysicists and other engineers to evaluate the geothermal developers' projects. So in addition to subsidize the projects, they could also be the investor. So eventually JOMEC becomes the venture capital company. They manage the geothermal subsidized projects as a business with the options to be the second largest share owner of the project they subsidized. In Taiwan, there is a major problem, that is that even the government subsidize 50% of the exploration and drilling cost. The developers are still difficult to get funded for the remaining venture since the investors hardly understand the business and don't want to take the risk even if it is small. This slide shows the feed-in tariff for geothermal power in Japan and its expected internal return rate. The procurement price per kilowatt-hour for geothermal power plant greater than 15 megawatts is 28 yen and 8 sen and 43 yen and 20 sen for those under 15 megawatts. The expected internal return rate is about 13%, which is the highest in their renewable energy sources. I listed the estimated developing cost per kilowatt and its selling price per kilowatt-hour for the geothermal power plants in different countries. The average developing cost of U.S. Geyser is the lowest. The site is very profitable even from the very low selling price. Of all the geophysical properties of rocks, electrical resistivity is by far the most variable. Values ranging as much as 10 orders of magnitude may be encountered, and even individual rock types can vary by several orders of magnitude. The figure illustrates very generally the conductivities or the resistivities of important rocks. The conductivities of the three geological targets are closely related to geothermal exploration. One is the conductivity of the clay cap rock. The second one is the conductivity of the aquifer. The last one is the phenomenon that the conductivities of the volcano rocks increased with respect to temperature. The magnetotelluric exploration is the most convenient method to obtain the conductivity distribution from very shallow about few tens of meters to few tens of kilometers. It uses natural electromagnetic sources. Hence is the most common exploration tool for geothermal exploration. Physical concept of magnetotelluric exploration is explained as followed. First, the natural electromagnetic field is from out space or thunderstorm very far away so that the field is uniform at the survey area. Second, the change of electromagnetic field will induce the electrical field on the Earth formation. Third, measure the electrical field and the magnetic field, or the change of magnetic field on the Earth's surface for a long time, at least 12 hours. Fourth, the impedance of the Earth formation at different depths could be obtained by the electric field divided by the magnetic field at a different frequency. The lower frequency for the electric field divided by the magnetic field represents deeper formation impedance. Fifth, from resistivity distribution, one could find the geothermal reservoir and build its conceptual model. One of the advantages of magnetotelluric array exploration is to use at least 3 simultaneously recording stations to identify the uncorrelated noise using variance techniques and Wiener filter to predict and replace the spike. One of the stations could be a remote reference so that it will take the advantage of the traditional remote reference magnetotelluric exploration method. Example of despike by variance technique for 4 simultaneously recorded magnetotelluric stations is shown on the slide. Red line represents the original time series data. The green line represents the noise removed for 114,000 seconds. This slide shows the comparison of magnetotelluric array against the traditional MT systems. 1. The most common magnetotelluric exploration used is by remote reference, assuming the reference site is with very small noise and the horizontal magnetic field is on the same plane wave. 2. The magnetotelluric array developed by 3J Tech was designed for improving the resolution of magnetotelluric readings in areas like Taiwan and Japan where the noise is high and land with enough open space is scarce. 3. 3J Tech developed the magnetotelluric array technology after more than 35 years of electromagnetic exploration experience in equipment, software development and field operation. 4. The basic concept of the magnetotelluric array is 1. Simultaneously recording at the sites with at least 3 magnetotelluric stations is applied to remove the uncorrelated local noises. 2. The identified noise is then removed through an magnetotelluric computer prediction filtering software, resulting in a higher signal-to-noise ratio. 3. The simultaneously recorded data are used for stacking to yield further higher signal-to-noise ratio and thus higher exploration resolution. A paper was published at World Geothermal Congress 2020+1 with title as, Comparison of Magnetotelluric Array Results with the Drillings in Taiwan. The YouTube link is as shown on the slide. We will skip this presentation. Anyone who is interested in learning the comparison could access the YouTube link. However, from the YouTube presentation, we concluded that the magnetotelluric array results show that the wells drilled by Chinese Petroleum Corporation and other government agents are located outside of the delineated possible geothermal reservoirs. This could explain why the drilled wells are not successful for the previous geothermal development. 3J Tech has developed a new control source electromagnetic exploration system, which has an extended linear ramp time. Its central loop transient electromagnetic survey uses smaller loop but deeper penetration. For civil or mining exploration, we could show the numerical modeling of using a small loop of 2.5 meters by 2.5 meters. The current waveform is represented by the next figure, which has 2010 and 960 microseconds for ramp up and ramp down respectively. The current at steady stage is at about 30 amperes. The total transmitting duration include both ramp times is 10 milliseconds. The advantage of 3J-Tech's extended linear ramp time central loop transient electromagnetic exploration system are 1. The central loop using extended linear ramp time could reduce the transmitter size but with deeper penetration. 2. From the numerical modeling we could see that the depth of investigations could reach more than 150 meters using a transmitter size of 2.5 meters by 2.5 meters by 8 turns. 3. By the same token, a transmitter size of 40 meters by 40 meters by 5 turns, the depth of investigations more than 2,400 meters could be expected. The potential application for geothermal are 1. Drilling site exploration for well design. 2. Detail reservoir exploration. 3. Reservoir monitoring while producing. This is the end of my presentation. Thank you for your attention. Please don't hesitate to contact me at wwj@3jtech.com.tw for any question.